PA2 going well? That was telling.
Absolutely. On schedule.
Okay. So I will be in the Digital Lounge tomorrow morning at 8, sorry. If you want to come by before my 9 o'clock hours, you can do that. And I'll be in my office at 9 as usual. Well, let me talk about 208 first. No, that was the other day. We already talked about that. So somebody pointed out I had a typo in here, so the test bed's actually just main 209, not main-209. It's going to be consistent, hopefully, going forward. I'm trying to update the readmes accordingly, but if you find typos, let me know. Okay, so ODP 209, it's another linked list problem. The linked list in this case does not have a sentinel node, so make sure you're not skipping the first node. You're writing a function called edit. It takes a pointer to the first node of the linked list, and it doesn't have a return value. It's returning void. And I'm guaranteeing to you that the argument I passed to you is not null. Okay, the argument I passed to you is actually the address of a node, which points to a second node, which points to a third node. And that third node points to null. So I'm passing you the address of a 3-node linked list. And what your edit function should do is delete that middle node. In other words, take the first node, have it point to the third node. And that's the whole requirement. So it's can be done in a couple of lines of C, or more if you want to use temporary variables. Yes?
Should we have it free the middle node?
I don't know if I require that, but shouldn't hurt to free it. All right, any questions about this? So you can get to the first node, that's PTR. You can find the address of the second node, how? PTR arrow next, yeah, next. And if you can get to the second node, you can get to the third node, it's second node arrow next. And so you can change PTR arrow next to be the address of the third node. So cobble that together and assess it. And that's due tomorrow morning. Do I want to post another one tomorrow? Yeah, I do.
Oh no.
I'll post one more tomorrow. I could, but I can only run one assessment at a time.
That's okay. Well,
I can post it ahead of time. I just don't want people to get confused, because then people start trying to assess 210 and it's trying to assess 209 and they get 0 out of 20 and they say, oh, it's not open, and they forget to reassess 209, and then I'm like manually changing.
Well, you'd always just put one line at the very top of the README that just says "Don't get confused."
Would that work?
That'll explain everything.
At the very top of the README of 210, just put "Do not submit it until."
I like "Don't get confused" better, because then the people who weren't here really
They
really get confused by that.
There we go. Don't get confused.
Just if they get all zeros, just put it.
No, they will be working on P2 by then. So. Everyone's working on P2 by then. So.
Read the terms and conditions.
Okay.
And just put "You have been warned."
Okay. Hopefully that stops people from getting confused.
I wouldn't know.
I really now want to go in and submit it.
Yeah, yeah. All right. So, and it's again the linked list of 3 nodes, no sentinel node, but you're inserting a node into the middle of the list. So, just more list manipulation. All right. So I got to remember to tell the other section that that's it. All right, any other questions? All right, let's talk about hashes. So, when I learned this, my teacher said hash is a kind of food that you get by taking a whole bunch of other foods and chopping them up and mixing them together. And you have to trust your chef a lot to be willing to eat it. I've never eaten hash. But it's a hodgepodge of things, and they're all jumbled together and mixed up, and you get a bowl of this stuff, and there's your dinner. And that's a little bit what a hash ends up looking like in a computer's memory in some sense. It's a way to store information in a computer, but the information is kind of jumbled around all over the place. Now normally, before 222, if we wanted to store something in memory, our best bet was an array. And the way we use an array is we store something in the first element, and if we have another thing to store, we put it in the second, and another thing in the third, and so on and so forth. And so arrays work well. They're not very efficient for retrieving information, right? 1,000,000 elements in an array, you might have to go through 1,000,000 things unless you can do a high-low search or something. Now most of the data we've been working with so far are numbers. And when we build a linked list, we're just making a list of numbers. Why are we doing that? I don't have a good reason. A friend comes up to you and says, hey man, I need a number. Can you give me one? You can go to your list and say, yeah, here's a 5. And they'll be like, thanks, I'll get back to you later. And then you can delete it from your list, right? But that's not a typical scenario. We don't usually just have a bunch of numbers stored. It's more common that we have multiple pieces of information that are associated with each other. So for example, we might have faculty information where we have a name and we have a department. And we might have Carol, and she teaches mechanical engineering. And we might have Izad, and he teaches electrical engineering. And we've got Nick, and I teach computer science. And we want to store this information in some sort of structure in memory. Well, one way to do this is to make a set of arrays. So we can have an array called name and give it a whole bunch of spaces. And we could have another array called department and give it a whole bunch of spaces. And let me put down the indices. And we'd like to ask a question like, for example, in what department does Izad teach? And we have this information in the memory of the computer. How do we figure out what department Izad teaches in? Well, you have to go through your name array and find Izad. And if that name never pops up, that person doesn't teach here. But we go through, that's not Izad. Hey, that's Izad. Where is Izad stored in here? Index 1. So now we go to index 1 in a parallel array called department, and index 1 has the entry EE. Izad teaches electrical engineering. So this is just parallel array structure. Well, the problem with this is efficiency. Because if we have 100 names and I'm looking for the person who was stored last, I'm going to have to check 100 entries to see if they match my name until I get to the last one, and then it'll say, oh yeah, there's that person, this is the department. or if the person I'm looking for isn't in this structure, I'm going to have to go through the entire array before I realize they're not in there. Now, if I can alphabetize, I could do some kind of high-low thing and cut my time down, and that gets a little better. But let's look at order of complexity. So, unordered array. This is what we call order n. N pieces of data roughly takes n operations to perform your search. If I can sort it, that can go down to log n. But remember, with log n, there was an insert issue. If it's unsorted, I can insert just by adding to the bottom of the array. If it's sorted and I want to insert, I might have to do n operations because I have to move everything down. So search is like that. Insert if it's unsorted, it's order 1. If it's sorted, we're back to order n. And I could use linked lists instead of arrays because we just learned about linked lists, right? And we know that the insert on a linked list is very efficient because we can just pop something into the middle. We don't have to shove everything down in memory. But the search is still a dog. We still have to start at the beginning and go through sequentially. We can't take advantage of this sorted thing. And we could try to do something like a tree, which we'll talk about in a few weeks. But parallel trees is kind of weird, and it's still order log n. So what's the ideal order of complexity?
Isn't it 1?
It's 1, or maybe 0. The practical ideal is 1. Order 1 means it doesn't matter how much data you have, it always takes one operation to perform whatever your function is. So I could search in a fixed amount of time regardless of how much data. 1 name, 100 names, 1 billion names takes the same amount of effort to search. And that's a really nice setup. And this is what a hash will approach. Yeah?
Same amount of time?
Same amount of time. I know, it seems ridiculous. We can kind of do this mechanically. I mean, our brain and our eyes do this. We can pick out a blue dot in the middle of a bunch of yellow dots without looking at each dot and saying, is it yellow, is it yellow, is it yellow? We can just look at an image and say, oh yeah, it's right there. Right? I don't know how exactly that works, but there's parallelism involved. But without any sort of biological trickery, we can approach this ideal of order 1. So here's an idea. The problem is we want to know what department Izad teaches in, and it's right here, but we don't know that index 1 is the magic location. We only know that Izad is stored in index 1 because we searched the name array for Izad. But if we somehow knew Izad is stored at index 1, Nick is stored at index 2, Carol is at index 0, and they said, what department is Nick teaching? You'd say, oh, well, Nick's at index 2, check index 2, go down to element 2 of the department, CS. Right? Took no time at all. The trick is, how do we know that Nick is at index 2 and Carol is at index 0? Well, that's what a hash does. So here's an idea. And I shouldn't be doing department because it's all one department actually. It's just engineering, bless you. But you know what I mean. So let's make a bigger array. Which goes up to element 26. So there's 27 entries in here. And here's our parallel array. Okay, let's store Carol, who teaches in ME. Let's store her information in this structure. I'm going to look at the first letter of Carol's name. That's a C. C is the third letter of the alphabet. So I'm going to go down to element 3. That's where I'm going to store Carol's name. And at element 3 in the department array, that's where I'm going to store mechanical engineering. And Izad, electrical engineering. So I is the 9th letter of the alphabet. So I'm going to go down to index entry 9. That's where I'm going to store Izad. And over here at entry 9, I'll say electrical engineering. And now I want to store Nick with computer science. I'm going to look at the first letter of my name, N. That's the 14th letter of the alphabet. So down here at index 14, I'll store Nick. And in the department array at index 14, I'll store CS. So my data is not stored sequentially from the beginning on down. It's scattered around these arrays. But with the following advantage. What department does Izad teach in? First letter is I. I is the 9th letter of the alphabet. Go to the 9th entry. Izad teaches electrical engineering. And even though there are 3 names in here, I didn't have to do 3 sets of operations. Okay, let's check Bob. What does Bob teach? Well, B is the 2nd letter. Let's go down and look at index 2. There's nothing there. Bob doesn't teach here. Okay, that's the basic idea. There's a ton of details here. And I can see some of you are already like ready to shout out, but what about? Right, there's details here, but this is the high level idea of a hash. Okay, we have a pair of sets of information. In this case, a name and what they teach. And based on the name, we've stored that information at a particular location in these arrays. And now if you give me a name, what does Izad teach? I can say Izad's 9th letter teaches E. What does Nick teach? N, 14th letter. Let's go to element 14. Nick teaches CS. Yeah?
Is that kind of like a two-dimensional index?
Kind of. In what sense are you thinking?
Like we have two-dimensional array. The left side is 1D, our side is 2nd.
Yeah, it's like that, but the addressing is a little different. Because we're not really yeah, we'll say more about it. But yeah, kind of. Okay, so there's some things we need to talk about. One, this business of what does Bob teach? Well, Bob starts with a B. Let's look at element 2. There's nothing in there. Bob doesn't teach here. This business of there's nothing in there is a little bit funny. Because I've told you before, there's always something in memory. There's no such thing as an empty memory location. I've drawn these boxes as not having anything in them, but if I were to check that entry in the array, it will have something in it. It may be random junk, but it's going to have something. So to know that this is actually empty, we need to have some kind of flag. So we're going to have, instead of just a name, we're also going to associate some kind of valid flag. And when there's a name stored here, we'll set that flag, and it'll be 0 everywhere else. So now when we check Bob, we check entry 2, check the valid flag at 0. We know there's not an entry in here. So that's not too bad to deal with. So what's the other problem with this?
It doesn't really improve the search algorithm. It's still order n, it's just n is the number of letters in the alphabet, right?
I'm not searching through 26 things though.
What, if someone else with a B in their name works here?
Yeah. But if you give me the name Nick, I look up the ASCII code for that first letter, I subtract 64 from it, right? And that gives me 14, and I just go to element 14. There's computer science. So it is an order 1 to look things up, but the problem is I can only have one person with the same first initial teaching in my school. So here comes Craig, who's highly qualified, but Carol's already teaching here. Sorry, Craig, can't teach her. All right, so that's not great. So we want to have a way to store Craig in this structure. So here's what we do. If we're going to store a name, we look at the first letter, we go down to that location, that's where we store it, unless somebody's already there. If somebody's already there, we're just going to store it in the next location. So if Craig comes along, we'd like to store them. So Craig, what does Craig teach?
Art history.
Art history, good. So Craig teaches art history. Letter C is 3. Should store Craig here. Check the valid flag. Oh, somebody's already here. Okay, we'll store Craig right here. We'll make that valid. And then at entry 4, we'll store art. Okay, so 2 things have happened. One, our insert has gotten a little more expensive. In this case, it took us 2 operations to store Craig. And our search is also going to be more expensive. If we're searching for Craig, we look at the first letter C, we go to index 3, we check the name. Is this Craig? No. Okay, there is somebody here, but it's not Craig. Since we know there's somebody here, we have to know that there could have been somebody else with a C that we tried to store here and they got stored after. So we have to go to the next location. And there we find Craig, index 4, there's Art. Yeah?
What if you have a Doug that was stored in index 4? Would you then just shift everyone down
Then you'd go to index 5.
and insert Craig in index 4?
So let's put Doug in. So what does Doug teach? Math? Okay. So Doug is a 4. Go to location 4. Oh, Craig's already in there. So let's go down to location 5. That's got a valid flag of 0, so set that to 1. Put Doug. And at 5 we put math.
I'm saying if now you want to insert a Carl, then would you shift Doug down?
Carl would go down to 6.
Oh, it wouldn't be alphabetical.
Right, so yeah, so it won't be alphabetical. So what does this mean for search? It means that when we search for somebody, we take their first letter that tells us where to go in our array. If we find a name there, we're done. The department's in the corresponding department array. If this is not the name we're looking for, but this is someone that we store, the valid flag is set, we got to check the next location. And if that's the name, we're done. If not, but the valid flag is set, we got to check the next location. So let's say we're searching for David, and I didn't leave enough space here after he's odd. Let's say we're searching for, let's search for Isaac. So Isaac is a 9. Come down to location 9, there's Izad. That is an entry in our table, but it's not Isaac. Go down to location 10. And the valid flag is going to be 0. There is nothing in location 10. That tells us Isaac isn't in our table. Because if we had stored Isaac, they would be somewhere after Izad.
So do you just put so much space in memory between like the different letters that you won't ever overlap onto the next letter?
Well, you could do that. So what we're getting to, and the answer to your question revolves around the idea of a hash function. So this business of taking the first letter and using that as an index, that's what we call a hash function. It says, how do we take a name and translate it into a location in this array? And this is a really, really simple hash function. Just take the first letter, find where it is in the alphabet, that's where we're going to store. And this is a really poor hash function, because everybody who starts with the letter C is going to get stored in the same location, and we're going to end up pushing these things down. So these things are called collisions. Okay, a collision is when two different names try to access the same location in your array. And if you never had collisions, everything would be order 1. It would be perfect. But it's impossible to avoid collisions unless your array is so big that it can store every possible name. And then if you write a very clever hash function, you can guarantee that there's no collisions. But that's not practical, right? 8-letter names, there's 26 to the 8th possibilities.
You just add another array at each index, so
You could add another array at each index,
make each one a two-dimensional, make it a two-dimensional array.
or
Linked list.
you can add a linked list at each index, and that's something we call chaining. And that's a very common way to do this. So each entry here, instead of just being a name, is a sentinel node, pointing to a linked list, and we would store Carol and Craig in this linked list, and we would store Doug and David in the next linked list, and Izad and Isaac in that linked list, and so on. And that's nice, because if you don't expect a lot of collisions, but you expect a few, we don't mind spending the order n search time to go through that linked list. And inserting is really quick. We can insert in the beginning of a linked list in a single operation. Make a new node, point it to the thing after the sentinel, point the sentinel to the new node. 3 steps. And when we get to deleting from a linked list is efficient also. So let's put down some terminology. So collision is when two names map to the same index. Chaining is the idea that each entry points to a linked list. And we're talking about names and departments, but this is a general concept. And more generally, this first field is called a key, and the second field can just be called a data or a datum. And so the idea is the key is what we use to figure out where our information is stored in this array, and then this data array at that same location gives us a piece of data that's associated with that key. So we always talk about key data pairs. Yeah?
So could we do it the other way, like who teaches computer science, and then we get Nick?
Yeah, so you could also key off of the department, and then go in with the department, find a name out, definitely. Yes?
If you would want to go back and say do like the first 2 letters.
So a better function would be to do something with the first 2 letters, right? So 26 squared, that's not too big, it's 500 something. So we could say, let's take the first 2 letters, turn that into, you know, a number from 1 to 500 something, and use that as an entry into the array. And that's going to give us fewer collisions, right? Izad, Isaac are going to not collide, Doug, Dave, and so on. That's a better hash function. Now we'd probably have first name, last name, right? At a bigger department. And so, you know, of course you might have 500 Bobs and 500 Carols, And if you're keying off of the first two letters of their first name, you're going to get lots of collisions. So you might switch to last name, but you might have a lot of people in your department whose last name starts with MC, Mick so-and-so, or you might have a lot of Smiths or Joneses. And so depending on the nature of the data, the keys actually, depending on the nature of those, you might want a different kind of hashing algorithm. So you might do something like take all of the letters in the name and add up their ASCII codes, and then reduce modulo 1000. And now you get a number from 0 to 999, and you could make these arrays 1,000 elements long. And so this is what we can generally describe as a hash function. So a hash function takes a key and it returns an index. Example. And you could take the first character of the name, that'll be its ASCII code, subtract 64. So A is a 1, B is a 2, C is a 3, and so on. And that would give you this hash function that we've been using here. A better example so just some summation, right? Add up all the characters in the name. So this will add their ASCII codes together. Take that final number and find its remainder when you divide by 101. Reduce modulo 101. And that'll give you an index from 0 to 100. So now we make our arrays 101 entries each. And very little chance that Bob Smith and Bob Jones will hash to the same location. So a good hash function will jumble things up, and two names that might look very close to us will end up pointing to very different locations in the arrays. A poor hash function leads to something called clustering. Clustering is many keys mapped near each other. And it's if you're using this idea of storing things in the next location or the next location, finding the next location that's free. Clustering is when you've got a bunch of things that wanted to get stored here, but you kept getting collisions, so you just stored them one after the other, and now you've got a big chunk of things here that all kind of collided with each other. And anytime you try to access something from a key in that range, you're going to have to go through an expensive search process. So probing which is something we do instead of chaining. So chaining is just make a linked list in each node. Probing is where we say, okay, if there's a collision, let's find another spot to store this piece of data. So probing says if you get a collision, find another place. Find another location to use. And that's what we were doing here. We tried to hash Craig, and it was supposed to go here, but that was in use. So we started searching for an empty location, and we found it in the next spot, index 4. So we stored Craig there. So what determines our hash implementation? the hash function is critical. The way that we're going to deal with collisions, whether we're going to do chaining or probing, is critical. The size of the hash table is critical. It turns out, for various reasons, if you make your hash table length a prime number, things work better. And there's tons of science and theory around hashing. What makes a good hash function. And it depends on your data. If you're hashing names, you may have a certain hash function. If you're hashing executable programs, you're going to need a different kind of hash function. Yes?
So you wouldn't really need any sort of sentinel key in this case, right?
No. So we can use this to store all kinds of things, right? Name and department is an easy example to pick on, but
in hash function better and like add, was it higher date,
say, oh yeah,
higher time, and then
yeah, you can add tons of information over here, and typically the data would actually be some kind of structure, right? Or maybe a linked list of pieces of information or something. The only thing that affects us is the nature of the key and what the hash function is. Once we know Carol is stored at location 3, we can just come over here and grab whatever is stored there. In Unix, when you type in something and you hit enter, if it's not a built-in command, it searches a set of directories for a file with that name. So if you say PA1, it searches through different directories to find a program called PA1. Now your path includes a dot in the beginning, so it searches your current directory and it finds PA1. If you say cowsay, it searches for a file named cowsay in each of the directories in your path. And when it gets to /user/games, it'll find cowsay in there. That can be a fairly expensive operation. If you look in all of the directories in your path, you'll find hundreds of files. If you just look in bin, there should be hundreds of files in there. So how does it efficiently say when I type in the command ls, how does it know it should go to user bin and find ls in there? It uses a hash. And this hash is built up in various ways, but ultimately when you say ls, there's something telling it where that program is stored. And if ls gets moved and I say ls and it's not there, then it needs to update the hash table. And then it's going to take longer. So sometimes the first time you run a program takes a long time, depending on how your path is set up. It's because it's got to go through and it's actually got to do the painful search, right? The order n thing. But once it's seen something, it'll put it into the hash, and now if you type in the program name, chances are you won't notice a delay when it runs. So these could be, directories where program names are stored. They could be the actual programs. You could have a hash with a bunch of binary executables in the data field. So you can do anything you want with this. The data is pretty, doesn't really come into play in most of this. It just kind of goes along for the ride. Alright, I'm going to keep that so we can come back to it. So one way to think about hashes is this idea of an associative array. And we talked about this a little in 224. Perl and SED and all these other tools have associative arrays built in. We can do associative arrays in C. There's a package called GDBM that basically implements a hashing type structure. And this is one of those, Thor hammers that you can use for everything once you make peace with it. An associative array basically lets us do array indexing with things other than integers. So if we have integer I, let me just do it like this. So I is an integer array. I can say I bracket 0, I can say I bracket 15, I can say I bracket 3, and I can get to different elements of I, but I have to use an integer, or something that turns into an integer, as an index. With an associative array, I can say something like I bracket Izad, or I bracket Carol. And it's like I have a piece of information stored in each of these entries in this weird looking array that I can index with names. This is what a hash, underneath this is a hash, right? This is how a hash can appear to us. I'm going to give you a name, you're going to give me a piece of information associated with that name. That's what an array is. I'm going to give you an index, and you're going to give me a piece of information. Let me do this. This doesn't match our table, but just work with it. Here I'm going to give you an integer, and you're going to give me a piece of information associated with that. And I'm giving you a 15 because that's the index where some person's name was stored, right? But here we've got a better kind of array. I'm just giving you a name and saying give me the piece of information stored at that location in the array. So entry Carol is ME, entry Izad is EE, and so on. So you can think of it as kind of this like super duper array that we can index with things other than just consecutive integers. And as I mentioned in 224, this is something our brains seem to do really well, right? Our memories are probably not stored in arrays accessed by integers. Because when you're trying to remember somebody's name, you don't start with your first memory and go through sequentially until you get to that person's face and then find what their name was, right? We don't know exactly how the mechanism works, but somehow the face takes us very quickly to the name. Or if it doesn't, we say hi and they say hi, and the voice takes us very quickly to the name or their hairstyle or something, right? So it's not a sequential search as far as we can tell. Something about the key tells us where that data is stored and we can go and retrieve it. So an associative memory, right? And this is really what a hash is kind of emulating. All right, so that's kind of a 20,000 foot view of hashing. Lots of details to get into, especially the hash function. And this question of probing, what do we do when there's a collision? Because going down to the next location is not ideal, right? Chances are that's going to lead to lots of clusters. What we'd really like to do is if we get someone with a C and we find that this entry is full, we'd like to try somewhere maybe based on the second letter of the person's name. So that Carol and Craig would end up trying the second one. CA would try down here, and CR might try down here. So that things get spread out and we make efficient use of the memory space. So we'll develop this hash function, and we'll add a second input to it, which we'll call a probe number. And we'll use that to put together some pseudocode for implementing a working hash. And next week we'll start doing some coding around hashes. I'll start some ODPs next week related to hash functions and such. And I don't know if PA3 will be hashes or not. I'm thinking about it. So we'll see. All right, so I'll see you next time.